All right, so in this video, we're going to be looking at how we can approximate the value or values of a function using what is called local linear approximation. So what does that mean? Basically, what we're doing in these types of problems is if we're given a function, we know that we can draw a tangent line, right? If we have some function like this, for instance, some sort of concave down function, we can choose any point here and draw, say, a tangent line that goes through that one point. And here, let me draw this a bit better. All right, let's see if we can redraw this. So let's actually start off by looking at the two types of graphs here that that we'll be looking at. So we can have either a function that is concave up, right, or one that is concave down. Concave down. So now what we're looking at here is if we choose some point along this function and we draw a tangent line, again, a tangent line intersects this function at that one chosen point. Hopefully I can draw a decent enough line. See, yeah, that's pretty good. So if we draw this tangent line, basically it's with local linear approximation, what we're saying is this line can serve as an approximation of this function, meaning we can see that if we choose a point slightly away from this tangent point over here, for instance, we can say that this point over here, this point, can serve as an approximation or is approximately this value on the original function. And that is true, right? We can see that it's a small gap. It is approximately there. But as we move further along the tangent line in either direction, we can see that the line continues to deviate from the actual function. So clearly, as we go farther along the line, it's no longer going to be as accurate. But if we are very close here to the original point on the tangent line, we can see that this line can serve as a rather useful or accurate approximation of our original function. So what we want to see here is that, or what we should acknowledge, is that this is in fact some estimate, right? We know that this is not the true value, no matter how close we may get. If I choose this point here, it looks approximately like it is even tangent. It is even a tangent point, but obviously it isn't. So it can be very, very close, which is also why we call this a linear approximation, is because if we zoom in on any function, even if we have a curve like this, if we continue to zoom in more and more, it will appear or begin to appear linear. So we can use that fact to our advantage here to try to approximate the values using the tangent line, but we need to know that this is an estimate at the end of the day. So what type of estimate is it? And what I mean by that is this value that we get, this estimate, is it greater than or is it less than the true value for our function? Right? Well, in the case of a concave up function like this, we can see that the tangent line always is falling below this function. And for that reason, we can say that any estimate that we formed with this tangent line for a concave up function is going to be an underestimate. An underestimate. Right? Because this line always is falling below this graph. So if I choose this point here, the value that we approximate, you can see, is underneath the true value. So it's always going to be an underestimate. Now in the case of, let's say, a function like this, which is concave down, in this case, if we say we choose this point over here, and we again draw a tangent line going through that point, that's close enough. We can see that, again, in this case, if we're using this line to approximate, this tangent line is always falling above our function. It's always above our function. So if I choose this point here, corresponding to this point, the true value of our function is less than or falls below the value that our tangent line would approximate. So if we're looking at a concave down function, it's going to always be an overestimate. The value that we estimate is always going to be greater than the true value for our function. So now let's see how we can actually use this to do some local linear approximations. So how do we know whether a function is concave up or down? That's actually something that we'll explore in a different video. But in any case, in the problems that we'll be seeing here, we'll be told if our function is concave up or concave down, which is also reminiscent of what you can see in some problems on the AP exam, as well as what you may see on your exams in college. But if we're told, for example, we have some function g, and this function g is concave concave down, and we're told that g of 3 is equal to 5, and g prime of 3 is equal to 4, we now are going to try to firstly start off by estimating. Let's try to estimate for g of 2.8, right? Using local linear approximation for our g at x is equal to 3. So in this case, we can see that the g, we're given an x value and a y value, input and output of this function, and we're also told that we're given the slope here at the value of x equals 3. This derivative of x of our function is telling us that we have a slope of 4. So using this information, we can start by creating, or constructing rather, the equation for our tangent line. And because we have this information, we know we can use our y minus y1 is equal to x times, is equal to m, which is our slope, times x minus x1. We have all of these values available to us, so let's just begin by constructing that tangent line. So we can see that y minus 5 is equal to 4 times x minus 3. So this here is going to be the equation for our tangent line. So all we now have to do is plug in the value that we are trying to approximate. Remember what we're doing here, keeping in mind, or kind of contextualizing what's happening here, is we're given this function g that is concave down. We're told that g of 3 is 5, and this g prime of 3 is 4. So if we say that this is our our point 3 on this line, we can see that we have now constructed this tangent line that passes through this point, right? That passes through our point here, g 3, 5. And this tangent line is what we're going to use to approximate the value of 2.8. So we're going to try to find the point 2.8 on this function. If this is 2.8, we're going to basically plug this in to our tangent line, this linear equation, and get what our y value for this tangent line at the value of 2.8 is, and that is going to approximate the value of 2.8 on our function g here. So hopefully that makes sense. So now really all we have to do is simply plug in the value of 2.8 into this equation for our tangent line. So let's just do that. We get y minus 5 is equal to 4 times x minus, we'll get our y minus 5. Y minus 5 is equal to 4 times 2.8, that's our value of x here, minus 3. So all we have to do here is solve for y, right? So our y minus 5 is going to be 4 times negative 0.2. Y minus 5 is equal to negative 0.8. So we get a y value here then of 4.2, right? We add 5 to both sides. So we get a y value of 4.2. So we're approximating our value for our g of x, or our g of 2.8, to be 4.2. So now that we have this here, what is the next part of this question that I was going to ask? So we know that our y is 4.2 using this local linear approximation. So now tell me, is this value here, is this an overestimate or an underestimate? And if you can explain why. Really, all we have to do in order to rationalize, or in order to explain our answer here, is refer to the fact that this is a concave down function. This function, or this graph, is concave down, so we can say simply that our estimate is n, because this is concave down, we know it's going to be an overestimate, is an overestimate because g of x is concave down. And that's all we have to say. Alright, so we can see that this is a very simple process here. A problem may ask you to do a little bit more work. For example, if we're given some f of x and we're given the actual equation, if we're actually given the actual equation, let's say some 5x minus 2x squared plus 3 or something, right? and we're told this is, say, concave down, and we want to find, at x equals 2, something like that, right? Well, if we want to first, they might ask us to find the tangent line. In this case, unlike in the last problem, we would first have to start by figuring out what our y values and our x values are, right? Or rather, we just figure out what the y value is by plugging this in for if you want to find the tangent line's equation, rather m times x minus x1. We would have to do a little more work to find these points here. We're given the x, but in order to get this y, we would have to plug in this x into our original equation. In order to get this m, we would have to take the derivative of this and plug in our x value. So it's just a little bit more work that would need to be done on our end. But other than that, the problem would then basically be done or approached in the same way that we've done the last problem. So it's just a couple more steps, but other than that, you should be able to figure it out as long as you're able to first find that equation of the tangent line. So that brings us to the end of this video. If you found it helpful, please show your support by liking and subscribing, and leave in the comments any questions you may have and what you'd like to see for future videos, and I'll see you in the next one.